All right, so we're going to do an example now of one of these center mass calculations. And if you've had calculus, which you have, you may have done this in your calculus class. Okay, so here we have a uniformly distributed triangular slab. So that means that the density is uniform, and as we talked about last time, we have to have uniform density. So we want to find the x center of mass. So really, our first order of business is to get rid of the dm. If we want the x center of mass, we want a dx here. If we want the y center of mass, we want a dy. Now, before we do anything, let's just look at it. I mean, most of the mass is distributed here and here. So if we want to get the x center of mass, it's probably going to be somewhere here. The y center mass is probably going to be somewhere here, right? And so, you kind of always want to do that before you actually do the calculation, because, I mean, if I were to get an answer over here, I know I'm wrong. And so you always want to think about it if your answer makes sense. All right, so here we go. Lots of steps, lots of math. So x center of mass equals 1 over the total mass integral x dm. Okay, now, as I said a minute ago, we've got to get rid of that dm. We want to get a dx. So we have uniform density. But this is a two-dimensional object, so the density is the mass divided by the area. Okay, all right, so uniform density. So that means that the total mass over the total area equals, okay, we're going to make a slice, right? We're going to make a slice because it's a two-dimensional object. We want to get a dx, so we're going to have a slice like this, right? So we have the dx. If we wanted to get the dy, we'd have to make a slice like that, so we get the dy. Okay, so the total mass over the total area equals, I like to call it the little mass, the mass of that slice, the little mass over the little area. I mean, that's what it means to have uniform density. So total mass over total area equals little mass over little area. Okay, so therefore we know that dm equals m over a dA. Well, okay, so we got rid of the dm, but I want a dx. Right now I have a dA. So that's kind of a problem. But before we worry about that, what's a? I mean, we can do this now or later. Might as well do it now. So A is the area of the triangle, which is just 1/2 base times height. So it's 1/2. Okay, the base is A. The height is B. All right. So we'll use that somewhere along the line. All right. Now let's worry. Okay. So we got our. So we know what A is. We know what M is. We know what A is. Now we got to worry about the dA. So what is dA? Well, like we talked about last time, dA is the area of this little tiny slice. We'll just look at it. dA is the length, which is y, times the width, which is dx. Now, awesome. However, there's a problem. This height y is not a constant, right? It depends on the x, right? I mean, if x is 0, the height is here. If x is a, the height is 0. So the height here varies with x. And if we're going to do an x integral, we've got to write y in terms of x, right? So we can do the integral. So basically, we've got to say, okay, we know that y is a function of x. We've got to figure out what it is. Well, luckily, it's just a straight line. So that's good. So we know from high school y, it's getting dark, y equals mx plus b is an equation of a straight line. So y equals mx plus b. Okay, so what is the slope of the line? Well, it's the rise over the run or the change in y over the change in x, whatever you want to call it. It's just going to be, and it's negative, right? So it's going to be minus b over a. So the slope is minus b over a. That's multiplied by x. And what's the y-intercept? Y-intercept is b. Okay, awesome. So now, we know what y is in terms of x. But, we have a b here and a b here. maybe it's nice to take out the b. It might simplify the math later on. So let's just do it. Factor out the b. So we get 1 minus x over a. You don't have to do that, but I think it's going to simplify the math. All right, so therefore, so the dA is y, which we just figured out, b times 1 minus x over a times dx. Awesome. All right, now I wish I had more room, but I don't. Okay, so let's see if we can do it. Here we go. So therefore, x center mass, 1 over m, integral x dm. dm is mass over area times dA. dA is b 1 minus x over a dx. All right. Now, what do you say we substitute for a? So we have a on the bottom, right? So a, this is, ab over 2. So therefore, 1 over a is 2 over ab. Let's just plug it in. What do you say? So 1 over a is 2 over ab. All right? That just, simplifies it a little bit. Okay, so what can we kill? So that mass kills that mass. This b kills that b. Anything else? Nope. We could take this a outside. All right. So let's make it look nice. So 1 minus x over a. Okay, so that's what we have. Well, let's multiply it out. So we have, I'm going to get rid of this. So we have 2 over a integral x minus x squared over a dx. Now, what are our limits of integration? Well, x goes from 0 to a. So we have 0 to a. So we have, whatever, over here. So we have 2 over a. Okay, what's the integral of x? X squared over 2. What's the integral of x squared over a? X cubed over 3a. And that's going from 0 to a. Awesome. So let me get rid of that. All right, so we have, so we have 2 over a. Okay, so plug in a. It's going to be a squared over 2. A squared over 2. Then plug in a here. It's going to be a cubed over 3a. So that means x squared over 3. I mean a squared over 3, right? Plug in the a. A cubed over 3a is a squared over 3. A squared over 3. Then you plug in the 0, it goes away. All right, doing great. All right, good, 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 good. Okay, we got to get common denominators, right? So multiply 3, 3, 2, 2. And then we get 2 over a. So 3a squared minus 2a squared over 6. So 3a squared minus 2a squared is 1a squared. So this is a squared. Okay, this a kills that a. 2, so we get a over 3. Right? That's the answer, a over 3. Does that make sense? Yeah, it makes sense. We expected it to be over here somewhere. All right, now listen. Do not memorize what I just did. That's ridiculous. All you have to do is use this formula, and then you're going to get rid of the dA. The dm. So you just keep working. You have to use this uniform density thing for sure. So you get this, and then the dA is just the area of this thing, which is not so bad, right? So the dA is just that. But then, you have to realize y varies with x, so you got to figure that out. Then you just keep doing it. So you just keep doing what needs to be done. That's all there is to it. Okay, there's nothing to memorize. Just keep working until you get an answer. Now, you only got to learn this by doing, right? So, I don't want you to do it now, but you, on your own, make sure you do it, calculate this. Right? I did this, you do that. And again, you want a dy over here, right? And so you're going to make your slice like this, right? So that's what you're going to use. Okay, so make sure you do that, and make sure the answer is reasonable. In fact, I'll tell you the answer. The answer is, okay, so here we had A over 3. The y center of mass is going to be B over 3, right? So B over 3. Kind of makes sense, right? Okay, so make sure you do it, because we're going to use this later on, so you have to know how to do it. Okay. All right, that was fun. Okay, different topic. A lot of different topics in this chapter. Like I said, we're going to use this method for Physics 220 also. So if you're planning on taking Physics 220, you better be comfortable with this. You know, once you do it a couple times, it's not so bad. All right, here we go. Now we want to talk about rotation about a fixed axis. So what am I talking about? So here, this is a fixed axis, right? It's not going anywhere. So this thing is rotating about the fixed axis. This would not be a fixed axis, right? Because the axis is moving. But here I'm holding the axis still. So we have rotation about a fixed axis. Okay. Now, we don't have to use a nice wheel. We can use anything. So let's use this, whatever it is, this blob. All right, this blob. So what we want to worry about is we want to figure out the kinetic energy. The kinetic energy of rotation. We know what, for translational motion, we know that kinetic energy is 1/2 mv squared. But, the blob is not moving, right? It's just rotating about a fixed axis. So we know we're going to come up with a different equation, right? All right, so let's do it. It's not so bad. Okay, so we want to get the total rotational kinetic energy. Okay, so let's be a little bit lazy. Let's just say there are 3 points. Even so, there's tons, right? I mean, there's gazillions of molecules making up this thing. We're just going to concentrate on these 3 points, M1, M2, M3. So this is the axis of rotation, or the axle. R1, R2, R3. As always, the velocity vector is perpendicular to the R, right? Okay, I mean, no kidding, right? Okay, so each particle in the object has kinetic energy as the object rotates. Got it. Okay, so you ready? Here we go. All right, so the rotational, so get to put a little R here just so you don't get mixed up, right, for rotational. So the rotational kinetic energy, 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus blah, 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 right? Okay. Well, gosh, I don't want to write that all the time. It's too much trouble, right? So that's the same thing as saying 1/2 the sum mv squared, right? So you're summing over I, so you have mi vi squared. Okay, so that's just a compact way of writing that. Now, wait a second. We're dealing with rotational motion, so I don't want to use v, right? I want to use omega. That sort of makes sense, right? So here's our good old formula that I keep telling you need to know. So v equals r omega. So we're going to substitute, okay? So let's substitute right here, I guess. So we have 1/2 sum over I, mi. Now, v equals r omega. So we're just going to say r I omega squared. Now, wait a second. Did I make a mistake? How come I didn't have to put a little subscript under the omega? Well, because, come on, isn't the omega here the same as the omega there, same as the omega there? Well, yeah, right? It's the same omega. So every point that makes up this thing has the same omega. So I did not need to put a subscript on the omega. So let's write that just a little bit differently. Let's, just to emphasize it, okay? Let's say 1/2, and then I'm going to say the sum mi ri squared. And then, since the omega squared is the same, I'll just put the omega squared there. All right? I mean, whoopee! I didn't really do anything fantastic, right? Okay, now, oh, I forgot behind there. Okay, this thing here has a name, and we're going to use it a lot. It's called the rotational inertia, I. Now let me write here. So I is called the rotational inertia, and it's a sum mi ri squared. Okay, and we'll get into it. Don't worry. All right, so that's the rotational inertia. Some people call it the moment of inertia, whatever you want to call it. I don't care. But wait a second. What's so awesome about that? Well, let's substitute. So we have 1/2. This thing is I omega squared. Okay, now hold on. For translational motion, kinetic energy is 1/2 mv squared. So look, I guess I got to put a T here, huh? For translational, just to keep them straight. So rotational, 1/2 I omega squared. Translational, 1/2 mv squared. So I, this I thing, it's kind of like the rotational mass. Because, you know, omega is the rotational velocity, right? And so I, like I say, I is like the rotational mass. Okay? All right, so there you go. So now we have the equation. For rotational kinetic energy, it's this, which is 1/2 I omega squared. And we're going to talk about this I, but just hold on, I will. Okay, so there's the formula. 1/2 I omega squared, just like 1/2 mv squared. And again, here's a nice way to look at it. So here's translational, 1/2 mv squared. So, you know, 1/2, 1/2. M goes to I, V goes to omega. So if you know this, you know, you kind of know that, right? It's kind of nice. Okay, so there you go. All right, now what's this I? What's this I, this crazy I? I mean, we're going to talk about it, right? Okay, first of all, this is a sum, right? You know, for like a small number of particles. Well, what if we have a very large number of particles? Well, guess what? You know, what do we always do? It becomes an integral, all right? So if you have point particles, this is a sum. But remember, what are we really concentrating on in this chapter? We're concentrating on rigid bodies, so this becomes an integral. Are you surprised? You better not be. I mean, so look at what we have again, this dm. So, you know, so those center mass calculations where we had to get rid of the dm, same thing here. So that's what I mean. You got to know how to do those center mass calculations. All right? Now, thankfully, for most common geometries, we don't have to calculate anything. We just have to look up the answer. All right? So here you go. So these are the rotational inertia, or moment of inertia, whatever, you know. So these are all the values of I for these different shapes and configurations. So, so look. So, you know, what does I depend on? I mean, here's a thin rod, but they have different values. Well, it's because this one is rotating about the center. This one is rotating about the end. See? Okay? Here's a slab, here's a slab. This one's rotating with the center. This one's rotating with the edge. Different values. Okay, here's a solid disk. Here's a hoop, right? And so different values, right? Okay, here's a solid sphere. Here's just a spherical shell. Different values. So I is more complicated. I mean, you know, for translational motion, we just have 1/2 mv squared. M is m. But for rotational motion, we have 1/2 I omega squared. I is really complicated, right? It's way more complicated than just m because it doesn't just depend on the mass. It depends on the shape of the thing, and where the axis of rotation is, okay? So, wow, you know. But again, I mean, you know, look at the definition. So I depends on the mass, but not only the mass, it depends on where the mass is located. If all of the mass is located far away from the rotational axis, this is going to be big. So look. So here, you know, the mass is just evenly distributed, right? But here, all the mass is far away from the axis. So you'd expect this to have a larger I than this. And by golly, you do, right? This is twice as much as that. Or here, you know, the mass is half, you know, it's spread over here. But now this one, you know, you have most of the mass is far, far away. And so that's why that is bigger than that. Same thing here, right? Here the mass is further away from the axis of rotation than it is here and here. So this is going to be larger than that. So this is just more complicated, right? What are you going to do, all right? Okay. Now, let's keep talking about this I. So yeah, you're going to use this table a lot. And I'll have this on the exams. You don't have to memorize this. So you'll use it in your homework and in your exams and in your lab as well. All right. So here's a review question. What? Okay. All right. Whatever. All right. You have two blocks. They're supposed to have the same size, okay? And they're at rest, and they're on ice. Now, one of the blocks is made out of super lightweight styrofoam, and the other one's made out of super heavy steel, okay? So, which one would be easier to move, or let's just say, which one would be easier to accelerate? The styrofoam, the lightweight styrofoam, or that heavy, heavy steel? Obviously styrofoam, right? And why? Well, because it has the smaller mass, right? This has much, much smaller mass than this. And remember, mass is the measure of inertia, right? So this has much, much less inertia than that, okay? So something that has a small amount of inertia, it's easy to change its motion, right? So it's easy to change the styrofoam. You just barely do like that. Whereas the steel, you got to, you know, it's harder, right? It's harder. All right, keep that in your head. Now we have two discs. Same shape, okay? Same shape. One is made out of styrofoam, one's made out of steel. But now we want to rotate them about a rod, about an axis, you know? So which one would be easiest to rotate about the axis? Well, obviously styrofoam. Why? Because it has the smaller rotational inertia. Remember? Right here, right? The mass everywhere, you know, the mass of every particle located at whatever R for styrofoam is much less than the mass of the steel molecules, you know? Okay? So the styrofoam has a smaller I, smaller rotational inertia. It's easy to rotate. Just like smaller mass, smaller inertia, easy to accelerate. So I mean, it's similar, you know, very, very similar. Okay, let's keep going. These are two of my grandkids, daughter-in-law. Okay, you have two wheels. This wheel, this is one of those machines that they use in a mine. And here's a bicycle wheel, carbon. So super lightweight. All right? Which one would be easiest to rotate about the axis? Obviously this. Why? Because it has a super smaller rotational inertia than this gigantic thing. Okay? All right. So that should make good sense. All right, let's there's something called the parallel axis theorem that is sometimes useful when you're talking about these objects. Now, all right, so you notice I covered this one and I covered this one. So every single object here, it's rotating about the center, right? They're all rotating about the center of mass, you know? Okay, so that's cool. Well, you know, what if I want to know what the rotational inertia is when you rotate these objects through an axis that's not the center of mass? What do I do? Well, what you do is you use something called the parallel axis theorem. Okay? So here's the parallel axis theorem. It's really nice and short and sweet. Oh, so here's this blob, right? And here's the center of mass. So this would be if we're rotating it through the center of mass, right? Axis through the center of mass. But let's say we want to know what the value of I is if we rotate it through some other axis. Now, this is called the parallel axis theorem. So this axis has to be parallel to that, all right? Okay, so they're separated by D, right? An off-center rotation axis. So here it is. It's pretty nice. The moment of inertia about some wacko axis, you know, not the center of mass axis, I is just I center mass, which is what's in that table, right? I mean, these are all I center mass, right? These are all I center mass. Okay, so the rotational inertia through some parallel off-the-wall axis is equal to the one you can look up, plus the mass of the thing times this distance squared. That's all. That's all it is. So, now, okay, so that's how you do it. All right, now, let's see. What I'd like you to do now is I'd like you to use this parallel axis theorem so to figure out the rotational inertia for this. So obviously, I center mass is this, right? So just use this equation, and this is I center mass, and figure out I for this, okay? So pause your video and figure that out, please. Okay, I'm assuming you've done it, so let's check if you did it right. Okay, so it says I equals I center mass plus md squared. Okay, so I center mass is this, right? Because this one rotates about the center of mass, so 1/12 ml squared. So 1/12 ml squared. And then mass is mass. And what's the distance? What's the distance from the center of mass axis to here? Just L over 2, right? So we have L over 2 squared, right? So L squared over 4. Well, let's get common denominator. So multiply that by 3, multiply that by 3. ml squared plus 3 ml squared is 4 ml squared. 4 ml squared over 12. 4 over 12 is 3. So we get ml squared over 3. Let's see if we did it right. Yeah, we did it right. Yay! All right, so there you go. So I mean, sometimes you need to know this. Or maybe, maybe they give you this, and you're supposed to find that. I mean, who knows? But it's just useful. So just keep it in the back of your mind. All right, so that's that. And that's a good place to quit.